This tutorial looks at the idea of relative atomic mass and how we can use figures from the periodic table to work out how much product we might get if we know how much reactant we're starting with. As usual, the specification content is on these black slides. As I'll be going through quite a lot of content in this tutorial quite quickly, it might be worth pausing on occasional slides just to make sure that you read through all of the information which is on the individual slides. When you look at the periodic table, there are two figures associated with each element. Here, for example, we've got 11 and 5. The 11 is the relative atomic mass of the atom, and that's the mass of an individual atom compared with every other atom. That's the one which we're going to be using on this tutorial when we're working out the mass of atoms and of compounds. Normally that figure, the relative atomic mass, is a whole number, but just on occasions there's a couple of elements which have got a number for the relative atomic mass which is a decimal, such as here chlorine, and that's because the relative atomic mass is actually the mass of an average atom, and chlorine has what's known as isotopes with different masses, and so we're working out the average mass of these isotopes, taking into account that there aren't equal numbers of each. So the mass of an atom we just read off the periodic table, but if we want to work out the relative formula mass, or the mass of a molecule or a formula, we have to work out how many atoms of each element are in that formula and then multiply each of those by their individual masses. So taking as an example sulfuric acid, H2SO4, this formula means that there's two hydrogens in the formula, there's one sulfur and there's 4 oxygens. So each hydrogen weighs 1, so 2 ones are 2. And each sulfur weighs 32, relative atomic mass 32, and there's one of those, so that's 132 is 32. And then there are 4 oxygens, and the 4 oxygens each weigh 16 each, 4 16s are 64, top them up and we get 98, and we call this the relative formula mass of sulfuric acid. Some formulas have a bracket, and what the bracket means is that everything inside that bracket is multiplied by the number outside the bracket, in this case the 3. So aluminium sulfate has got 2 aluminiums, because the 2 is directly after the Al for the aluminium, but instead of there being 1 sulfur and 4 oxygens, there's actually 3 sulfurs and 3 fours are 12 oxygens. So when we add up the relative formula mass of this, each of the aluminiums have a relative atomic mass of 27, so 2 27s are 54. There's 3 sulfurs, each weighing 32, so that's a 96. And as we said, 3 lots of 4, 12 oxygens, 12 lots of 16 makes 192, so the whole formula works out at 342, the relative formula mass. Here's a past paper question on this subject. Potassium nitrate's a fertilizer. How many different elements are there in potassium nitrate? Well, here we look at the number of capital letters. There's 3 capital letters, K, N and O, so the number of elements is 3. Working out the relative formula mass, we've got 1 lot of potassium, we've got 1 lot of nitrogen, and we've got 3 oxygen atoms. So 1 potassium is 139, which is 39. 1 nitrogen is 1 lot of 14, which is 14. And 3 oxygens is 3 lots of 16, which is 48. And when we add up 39, 14 and 48, we end up with a total of 101. And as you can see from the mark scheme, there's the answers, 3 elements, and the mass is 101. Here's another similar question. Look at the table, it shows some information about 2 fertilizers. It gives the name of the fertilizer, the formula and the relative formula mass. So the ammonium nitrate is worked out for us, but the ammonium sulfate, well, when we look at its formula, we'd see it would have 2 nitrogens, 8 hydrogens, 1 sulfur and 4 oxygens. When we top these up, we've got 2 nitrogens weighs 28, 8 hydrogens weighs 8, 1 sulfur is 32 and 4 oxygens weighs 64, and the total of these is 132. And there we have the answer from the mark scheme, 132. And some more parts from the specification. We need to know that the total mass of the reactants is the same as the products. This is the principle of conservation of mass, and explain why that is, and also use chemical reactions in order to work out the mass of products based upon the mass of the reactants that we've started with. So the conservation of mass states, and you need to know this definition, that the total mass of the products equals the total mass of the reactants. And if we use an example here of the reaction between iron and copper sulfate to make copper and iron sulfate, if we work out the relative atomic masses of iron and copper and the relative formula masses of copper sulfate and iron sulfate, then we can work out with a balanced equation here that the reactants together weigh 215.5 and the products here weigh 215.5, which should be as no great surprise. And the reason for this is that there are just as many atoms of each reactant as there are of the products. You may have to do that yourself in an exam question and to explain why mass is conserved in the chemical reaction. This all comes down to the fact that atoms can't be created or destroyed and only can be rearranged in chemical reactions. What the examiners expect you to be able to say is that there's the same number of each atom of the reactants as there are of the products, and you can see this in the graphic that in that reaction that we just looked at, the iron and copper sulfate makes copper and iron sulfate, and you can see that we start off with one iron, we start off with one copper, we start off with one sulfur and 4 oxygens, and in each case we end up with those as well. So because there's the same number of atoms of each element at the end as there is at the beginning, there's no change in mass. Now on to the mathematics, the use of simple ratios or logic to work out how much product you'll get if you know how much reactant you've started with. And this of course relies on the same principle, the conservation of mass, that the mass of the product is always going to be equal to the mass of the reactants. So a product that you might do in school is to heat up some copper carbonate. So you start off with a weighed amount of copper carbonate in a test tube, and you would then heat it strongly to drive off the carbon dioxide to make it into copper oxide, and then weigh it again. The difference in the two masses would be the mass of the carbon dioxide which has come off. Let's put some figures into this. The copper carbonate, which is CuCO3, would break down to copper oxide, which is CuO, and carbon dioxide. And if we had started with one formula mass of copper carbonate, which is 123.5, we would have ended up with 79.5, which is the relative formula mass of copper oxide, and an amount of carbon dioxide. Now, if we'd heated up that amount of copper carbonate, what mass of carbon dioxide would have been lost? Well, through the principle of conservation of mass, the mass of the product must equal the mass of the reactants. Therefore, the mass of the carbon dioxide would be 123.5, take away 79.5 grams, which would work out at 44.0 grams. And now using logic, if we heated only 12.35 grams of copper carbonate, what mass of copper oxide would we have got? Well, 12.35 grams of copper carbonate would be exactly 1/10 of that amount. So you'd expect to get 1/10 of the amount of copper oxide. In other words, 7.95 grams. So the answer to this would be 7.95 grams. And now we move on to a second type of experiment here where a mass of oxygen reacts with a known mass of magnesium to make magnesium oxide. You might have done an experiment like this where some magnesium ribbon is weighed in a crucible and then heated strongly to convert it into magnesium oxide. The mass goes up because the magnesium will react with oxygen from the air to make magnesium oxide. Now here's an example calculation based upon that experiment. If I'd used 24 grams of magnesium and heated it in oxygen, I would have made 40 grams of magnesium oxide. Now, if we'd heated that 24 grams of magnesium, what mass of oxygen would have been gained? Well, again, by the conservation of mass principle, the mass of the reactants must equal the mass of the products. So the mass of oxygen must have been 40 grams, take away 24 grams, in other words, 16 grams. But if we'd only heated 2.4 grams of magnesium, what mass of magnesium oxide would I have made? Well, 24 grams makes me 40 grams of magnesium oxide. So if I'd only used 2.4 grams, that's 1/10 of the amount, I'd have only got 1/10 of the amount of the magnesium oxide, which by logic would be 4.0 grams. Here's an exam question based on this principle. Look at the equations. They show what happens when calcium carbonate's heated. The calcium carbonate makes calcium oxide and carbon dioxide. And Janice heats up 50 grams of calcium carbonate. So here we've got 50 grams of calcium carbonate on the left. And it says, what's the total mass of the calcium oxide and the carbon dioxide on the right? Well, by the principle of conservation of mass, this would also be 50 grams. Janice heats 60 grams of calcium carbonate instead of 50 grams. How does the mass of the calcium oxide she makes change? Well, if you're using more calcium carbonate, you'd get more product, so it would increase. And there are the answers to those questions. 50 grams of product and the mass of calcium oxide would increase. And finally, another two questions. This question is about chemical calculations. Jake and Monty make iron sulfide. They heat a mixture of iron and sulfur here in the test tube. Look at the equation for the reaction. Fe plus S gives FeS, and iron plus sulfur gives iron sulfide. Calculate the relative formula mass, the Mr, of the iron sulfide. Mass of iron is 56, sulfur is 32. Well, iron sulfide contains one atom of iron and one atom of sulfur. The one atom of iron would be 1 times 56, which is 56, and the one sulfur would be 1 times 32, which is 32. We'd add them together and we would end up with 88. So the relative formula mass is 88. Now, remembering that figure from the previous question, look at the equation for the reaction again. Jake and Monty start with 5.6 grams of iron and 3.2 grams of sulfur. What mass of iron sulfur would they make? Well, there's two ways around this question. We could remember that 56 and 32 gave us 88, so 5.6 and 3.2 by the theory would be logically a tenth of 88, which would be 8.8 grams. The other way we can look at this is by the conservation of mass. If we'd started off with 5.6 grams of iron and 3.2 grams of sulfur, then the total mass of the reactants would be 8.8 grams. And that would mean that the total mass of the products would also have to be 8.8 grams, which is the iron sulfide product. And there's our answer, the relative formula mass for the iron sulfide being 88, and the mass in this case being 8.8 grams.